Welcome friends, this is the next lecture on acoustics and noise control. So, till now we had been studying the acoustic plane waves in particular. We have formulated the equations, we have looked at the solutions, we had also looked at a very important application of acoustic plane waves which applies in industrial application for muffler design. We had quite elaborately discussed the procedure of muffler design based on plane wave theory, but now in the remaining part of the course we will quickly run through the 3-dimensional acoustics and in particular the spherical waves. So, the topic of this last module is 3-dimensional acoustics. So, towards that end we start again with the governing equations of acoustics. You will recall that we had derived the governing equations of acoustics in the early part of the course, and that equation was derived in a completely general 3-dimensional settings. So, the equation if you recall was given in this form: del square p is equals to 1 by c square del 2 p del t 2. Okay. So, we will start from here and we will develop the 3-dimensional acoustic wave solution just as we did for the 1-dimensional case. So, in the 1-dimensional case, again to recall, in 1D acoustics we simply simplified this Laplacian operator to be the second derivative with respect to our space coordinates, which was defined as x. So, what we will now firstly look at in 3-dimensional acoustics is the category of spherical waves. Okay. And in spherical waves, as the name suggests, the wave fronts are no longer planar. So, what we will expect is that all points on a spherical surface this time, and since I cannot draw a sphere in my plane of the tablet, I would rather draw a circle, but you should understand this is actually a sphere which is drawn. So, all points in this sphere will have identical pressure, identical velocity, identical intensity, all quantities of interest. So, just like in a plane wave we define all quantities of interest are identical in planes, and these planes happen to be normal to the direction of wave propagation. Exactly the same way for spherical waves, all points on a spherical surface have identical acoustic pressure, acoustic velocity, and everything related to acoustics is same at these points. So, thus we say that the wave fronts this time are spherical. So, in contrast to the planar wave fronts which we studied in plane waves, now we will study the spherical waves which bears spherical wave fronts, and towards that end we will change over now to a coordinate system which is spherical. So, you will recall a spherical coordinate system is indicated by an r theta phi specification, where r is the radius vector, theta is this angle, and when you drop a perpendicular, then the angle that is subtended in this plane would be marked as phi. So, r theta phi are the variables in the spherical coordinate system as opposed to x y z in the Cartesian coordinate system. So, we will start from the solution of the governing equations of acoustics in 3D, but in a spherical coordinate system, because we are looking for a spherical wave solution in our case. So, here is what we will do. So, we will try to solve del square p is equals to 1 by c square del 2 p del t 2, and del square is the Laplacian in the spherical coordinate system. And this expression for Laplacian in a spherical coordinate system is available in any book on engineering mathematics. In particular, I will refer the book by Krzyk, Engineering Mathematics by Krzyk. It has the expression for the Laplacian in spherical coordinate system. So, I do not wish to derive this expression. So, I will simply give you the result, which is del square p in the spherical coordinate system will be written as del 2 p del r 2 plus 2 by r del p del r plus 1 by r square sin square not sin square sin theta 1 by r square sin theta del del theta sin theta del del theta plus 1 by r square sin square theta del 2 del phi 2, and there is a p here, there is a p here. So, this is the expression for the Laplacian of the variable p. Acoustic pressure is given in this form once you open it up in the spherical coordinate system r theta phi, and r theta phi is as indicated in this diagram. Now, going forward we realize that we are looking for a spherical wave solution, which means there is absolutely no dependence in the angular variables. All points on this sphere will have identical acoustic pressure, that is after all the definition of spherical waves, and therefore, if all points have got to have the same pressure distribution at a particular radius, it cannot have any dependencies with the theta variable or the phi variable. So, therefore, as we are looking for spherical wave solutions, we can happily set these two conditions to be 0, which implies that there is no dependence of any angular variables. Okay. So, with that being the simplification, now we can look to solve this simplified equation, which is del 2 p del r 2 plus 2 by r del p del r is equals to 1 by c square del 2 p del t 2. Okay. And what we can now do is we can open this term a little further to give us del 2 p del r 2 plus 1 by r del p del r plus 1 by r del p del r is equals to del 2 p del t 2 1 by c square. So, what I will do is I will multiply throughout by r and get it in the following form. So, if I multiply throughout by r, I get r del 2 p del r 2 plus del p del r plus del p del r again is equals to 1 by c square, and the r multiplication here can be carried within the differentiation process. After all, the space variable, which is the variable r, symbolized by the variable r, does not lead to any problems here, because del r del t is 0, that is space variable and time variables are independent. So, this step should be perfectly valid as far as the mathematics is concerned. Next, we can group these terms in the following fashion. We can write it as del del r of r del p del r, because r del p del r is going to give, when you differentiate it, it is going to give the first term as r del 2 p del r 2, and del del r of r is just 1. So, this is the second term arising out of it, plus del p del r again is equals to 1 by c square del 2 del t 2 of p r, and this we can further simplify in the following fashion. we can collect the differentiation process together and then write r del p del r plus p, right. This is the left hand side of the previous step, and that is equals to 1 by c square del t 2 p r. So, we have to simplify this a little further. So, I will just copy paste this equation in the next page to make that simplification happen. So, again I restart from this last step and let us see what the next step leads us to. So, in the next step I realize that the quantity under the bracket is nothing but del r of p r. So, again this is a product of two quantities p and r. So, when you take the differentiation with respect to r, the first quantity you will get is r times del p del r, and the second quantity you will get is p times derivative of r with respect to r, which is unity, which is exactly what is shown in the previous step. So, this simplification should also be justified to you, and finally, we get it, the right hand side is as it is. So, this equation in turn implies that I have to actually take second derivative of the p r variable on the left hand side, and that is essentially equals to 1 by c square del 2 del t 2 of p r. So, the final equation that I am looking to solve after all this simplification for the spherical waves looks like this. Okay. So, here you will realize this equation is identical to the plane wave equation, except for the change that instead of p r you had p in the plane wave equation. So, I will just make a recall here. So, recall the plane wave equations were derived to be del 2 p del x 2 equals to 1 by c square del 2 p del t 2. So, the only difference between the plane wave equation and the spherical wave equation as we have derived lies in the fact is in the that the space variable x has been replaced by the radius variable r, and instead of solving for p, we now can solve for p times r. Other than that, everything else is just the same, and we will also recall the solution of the plane wave was derived with D'Alembert solution, and everything was derived as p equals to f of c t minus x plus g of c t plus x. Okay. So, this was our solution for plane wave equation. The equation itself was stated as I have given here. So, therefore, by analogy, with plane wave equation, we should be able to construct the solution for the spherical waves in without any trouble. So, that is what we are going to do. So, that by analogy with plane wave equation, the solution of the spherical wave equation is therefore given as so this time it is going to be p r, which is going to be my variable of interest, and p r will have an identical type of solution like a plane wave. Okay. Just that the variable x will get replaced by the variable r, and therefore, if p is our quantity of interest, the final solution for p is now pretty trivial to contemplate. So, the solution for p can be written as follows. So, all that we have to do is to divide the r over here on the left hand side. We instead of multiplying by r, we multiply the right hand side with 1 by r, I mean we divide the right hand side with r. So, this is the solution for the plane wave equation. So, this is the solution for the spherical wave equation. So, this is the solution for the spherical wave equation. So, this represents waves which are completely symmetric, which are dependent only on the radial coordinates, does not depend upon the angular coordinates, and the characteristic of this wave is this, that all points which lies at the same radial location have got identical pressure, identical velocity, identical intensity, everything. If pressure is same, velocity is after all derived from the pressure through the Euler equation. So, therefore, if pressure is same, velocity also has got to be the same, intensity is also have got to be the same. So, therefore, what I have presented to you is that the spherical wave equation is an easy fallout if you can understand the development of the plane wave equation. Spherical wave equation is a very smooth transition, if not an easy transition. Okay. So, let us carry on to understand the interpretation of these two solutions. As was talked earlier, this represents, just like in the case of plane wave, in the case of plane wave we understood that this represents an outgoing wave or a forward wave, and this represents an incoming or backward wave, right. F and G has these characteristics. Now, here also the same rule applies, except for the fact that as it goes out or comes in, the amplitude no longer remains constant, but it has it varies in proportion to 1 by r. But firstly, let us make this observation that this first term is associated with outgoing waves, and the next term is associated with the incoming waves. And also we will make this observation that in contrast to plane waves, which propagate without any change in amplitude, spherical waves propagate with a changing amplitude or a varying amplitude. The amplitude varies in proportion to I should say inversely proportional to the radial distance. Radial distance. So, this is very useful that the amplitude by itself is going to have a fall. If I just plot the amplitude, it will have a 1 by r decay. So, the amplitude against distance. So, this is the distance which is from the origin where you are interested. So, the distance, as the distance from the origin increases, then the amplitude is seen to fall. This is very interesting in terms of applications. So, in terms of plane waves, what we understood was that the amplitude being constant, we had to put in a muffler such that we get some reduction of the amplitude at the point where the exhaust is opening out to the atmosphere. But in case of spherical waves, it so happens that as the wave is spreading, as the wave is going to going to distances which are farther off, then the wave itself suffers a drop in amplitude, and that essentially means that the noise associated with these spherical waves will drop drastically as you go a little farther away from the source. Okay. So, in terms of noise control applications, it has got huge implications. One way by which you can appreciate this result is by by recalling something which you very often do in your everyday experiences. When you actually put your earphone onto the ears, then you are reciting the earphone plays out a sound such that the radial distance between the location of the sound and your eardrum is very minimal, which is why the earphone when inserted into the ear is actually producing a very appreciable quantity of music, and sometimes it could be very loud music also. But hold the earphone just away from your ear and the sound is barely audible. So, what happens at that time is that when you are holding the earphone just away from your eardrum, you are occupying a position as indicated by this red line. So, here you see you have now encountered a drastic fall in the sound level. So, therefore, you cannot hear the music if you happen to hold the earphone away from your ear, but even if it is very close, but away from your ear, there is a drastic fall in the sound level and you cannot hear it any longer. What happens in a speaker on the other hand, when you are hearing a sound through a speaker as possibly you are at this time, in that case we are talking about two. If you are hearing music from a speaker, then possibly you are already standing far away from the speaker, and then if you go a little bit further, then you possibly are at, let us say, this position, and between these two positions there is hardly any difference in the amplitude of sound. So, once you are your baseline is already far away, then going a little farther away does not create much of a perceptual difference in terms of perception of sound. But if, as in the first example, if the baseline, or if you are referencing your sound measurement with respect to the situation where the sound is produced at almost very close to your eardrums, then obviously it will be very loud. But once you increase the separation between the eardrums and the place where it is produced, in this case it is the earphones, then you will find a drastic fall in the sound levels, and that drastic fall could actually mean that the sound is not even audible to your ears. So, this has important ramifications as I explained. So, what I will now do is that from the pressure expression that we have obtained, we will go to the velocity expression, but before that, just like as we did for plane waves, we will now no longer take an arbitrary time dependence. Remember, in the development of the plane waves, we first took the time variable into consideration, but then we said we will be interested only in a harmonic time dependence, because that is what leads to steady state noise. And in case of harmonic time dependence, we found that the solutions are much easier to handle, and yet it has got very many applications. So, therefore, we will introduce from here on, we will be introducing the harmonic time dependence, which again to recall, and this implies any quantity of interest I mean it is mostly the pressure and velocity. I would rather be specific by saying pressure and velocity, or even more specifically pressure and particle velocity has a time dependence of the form of e to the power I omega t, as was again done for plane wave theory. In plane wave theory, we said that all the pressure, we assume that the pressure does not have an arbitrary time dependence, but it has a time dependence which is harmonic, and that essentially meant that any pressure at for plane wave p x comma t, we said is given as p x into e to the power I omega t. Same we will do for the spherical waves also, just that we will replace the x variable with the r variable, r denoting the radial location. So, and omega is the frequency in the, it is a circular frequency rather than the frequency which is reciprocal of the time period. So, this is circular frequency and you know what that means. So, with this substitution we can appeal to the Euler equations, which again is a general equation for a fluid, and that stated that mean density times del u del t should be equals to minus of gradient of p, where u is the particle velocity. So, we derived this equation in one of our very early classes. I will just recall that result for you at this stage. What we need is the radial velocity at this point, because we are talking about a spherical wave. When we are talking about a spherical wave, please understand again from the figure that all particles will have to move only in the radial direction, because of the symmetry, there cannot be any angular motion, because any angular motion of the particle will break the symmetry of the problem. Everything should depend only on the radial coordinates, and therefore, the radial velocity alone should be non-zero, the other angular velocities should be 0. That is again coming from the symmetry arguments. So, if we specialize this equation towards the radial velocity, this is what we will get. Gradient of p will be simplified to del p del r. But now, since all variables of interest are having harmonic time dependence, we can write del del t equivalent to I times omega and rho 0 stays times u r to be equals to minus del p del r. And we already know that p of r has got to be of this form, f of C t minus r plus g of C t plus r. So, let us consider the outgoing wave to start with. So, we will consider the outgoing wave, and the outgoing wave form will be given as, so the outgoing wave with harmonic dependence, just like we did for plane wave. So, in the plane wave case, we replace this C t minus r to basically omega t minus k r, where omega by k turned out to be c. Exactly the same thing we are repeating now. So, with harmonic dependence, p at any radial location will be given in this form, e to the power I omega t minus k r by r plus b by r e to the power I omega t plus k r. But then we said that we are not going to look at incoming wave. So, this is the incoming wave. If you are interested only in the outgoing wave, you should take only the outgoing wave term, which is, this is the outgoing wave term, the other term is the incoming wave. So, for the present derivation, we will take only the outgoing wave term, which reads as P r is equals to a e to the power I omega t minus k r. So, when we make this substitution here and we calculate the del p del r. So, if p is equals to a by r e to the power I omega t k minus r, and e to the power I omega t will be suppressed from here on, because again this is in consonance with what we did earlier for plane waves. We just suppress this for brevity. E to the power I omega t is implied, we do not have to write it again and again. So, therefore, we write this in a short form as P r e to the power minus I k r. So, this is the harmonic outgoing spherical wave. Okay. So, let us do a little bit of analysis related to this equation. So, if P r is a by r e to the power minus I k r, then del p del r is given by minus a by r square e to the power minus I k r minus I k a by r e to the power minus I k r. And if we take minus a e to the power minus I k r by r as common, then what we will get is the following 1 by r plus I k. Okay. And from the Euler equations what we need is the following. We need rho 0 I omega rho 0 into u r must be minus del p del r, which now reads as a e to the power minus I k r by r into 1 by r plus I k. Okay. But then this group of term a e to the power a by r e to the power minus I k r is nothing but the pressure at the location r. So, that change we will make, and as a result we will get to see 1 by r plus I k. So, then in the next step what we will do is we will recall that omega by c is k, and as a result I rho 0. So, instead of writing omega I will write it as c times k u r will be equals to p into 1 plus I k r by r, and that too in the next step we will see as p by u r to be I rho 0 c k r by 1 plus I k r. A little more simplification, rho 0 c times I k r divided by 1 plus I k r, which could also be written as rho 0 c 1 divided by 1 by I k r plus 1. So, this is very crucial result, that for outgoing harmonic plane waves, not plane waves, spherical waves, we have this crucial result, which is the pressure denoted by P, acoustic pressure denoted by P divided by radial particle velocity denoted by u r. Okay. That quantity is turning out to be rho 0 c into 1 plus 1 by I k r plus 1. We identified this sort of a quantity, pressure by velocity, in our earlier analysis as impedance. So, we will continue doing so. So, we will call this quantity as the characteristic impedance of spherical waves, of spherical wave, and that turns out to be rho 0 c multiplied by this quantity, and rho 0 c you will remember is the characteristic impedance of the plane wave. So, the characteristic impedance of the plane wave and the characteristic impedance of the spherical wave is related. Okay. And the relation is given in this equation. What we can quickly note is that if we have the situation that k r is large, k r is going large, which means that this also implies that 2 pi by lambda into r is a large number, which means that the distances that we are looking at is much larger than the wavelength of the acoustic wave that is propagating, and wavelength again has the same connotation. It basically means the distance between the two maxima or the two minima of the wave. So, if you have the situation that the distance is far greater than the wavelength, then you will land up into this situation that K r is a large quantity, and if K r is a large quantity, then 1 by I K r will become a small quantity, and therefore, the characteristic impedance of the spherical wave, which I can call as Z S P, will be same as the characteristic impedance of the plane wave. Z S P will tend to Z P. So, spherical wave impedance will approach the plane wave impedance. So, in other words, let me just consolidate the findings. What we have found is that as the distance from the source increases, the pressure is going to fall off, and therefore, when you are talking about distances which are large, at very large distances, let us say this zone wherein you have this condition coming in that K r is large. So, here let us say K r has gone much greater than 1, which is like it is going towards infinity. So, here you see that the acoustic pressure amplitude. So, this is the plot of pressure, by the way. Here we can say that the decay in this region of space for the acoustic pressure is minimal, and also the impedance in this region we will say is almost approaching the plane wave impedance, because K r is large. If K r is large, we have seen that the spherical wave impedance has become the plane wave impedance. So, if the impedance is same as rho naught c and the pressure is not dropping, that means we essentially have the plane wave condition, that is the velocity in the direction of propagation of the wave will be given by rho naught c multiplied by the pressure, and that is exactly the same situation that we had in plane wave. So, thus in the region K r much greater than 1, we have minimal decay of the acoustic pressure amplitude, and also we have the plane wave, we have the impedance to be approaching rho naught c, which is the impedance of plane wave. So, therefore, the particle velocity in the direction of wave propagation, which was u r, is basically rho naught c times the acoustic pressure, and the same formula is obtained was obtained even for the plane wave. So, in this sense, spherical wave propagation at large distances away from the source is basically boiling down to the case of plane wave propagation, and that is why we spent the major part of this course in the analysis of plane wave propagation, because usually more often than not we are interested in the propagation of the sound which is quite far away from the source. So, where you will usually have this condition K r much greater than 1 to be satisfied, and at least in that cases you can completely rely on the plane wave analysis to give you good approximate answers. So, thus if K r is large, then plane wave conditions are approximated by the spherical wave. Okay. So, that is really nice that all our analysis for for plane waves carries over to this case also, together with some I mean it is not exact, that is understandable, but at least it is approximate. So, we can hold on to that part of the analysis. The other point which I must elaborate is about the incoming radial wave solutions. So, you can understand that if you have something like a sphere which is pulsating radially in and out. So, we have this balloon like object, balloon like structure, if you may so call it, and just like heart beating, it is pumping in and out, and contemplate this situation that this balloon like object is there in the complete 3 dimensional place R3. So, there is only one object which is this balloon like object which is pulsating radially inward and outward, and there is absolutely no enclosures, no barriers, nothing. So, you can expect that it will lead to outgoing radial waves, right, and these are exactly the outgoing spherical waves that we have talked about. And as the wave propagates, there is a decay in amplitude in proportion to the distance from the center of the sphere, and also as you go to distances farther and farther away, then you get to the condition where the impedance of the spherical wave approaches that of the plane wave, and thereby you get your plane wave conditions to be approximated very nicely. But what happens on the other? So, this was the outgoing wave solution. If we simply contemplate the situation of a time reversal, that means if we have, just like there can be an outgoing wave solution, there can be mathematically an incoming wave solution also. Remember, this happened even in the case of plane wave. In the plane waves also, when we did the problem of a duct which is infinite and then we had only one excitation, mathematics showed us that there could be a forward wave, there could be a backward wave. But then we applied our physical logic and physical intuition associated with the problem, and then we said that no, the incoming wave is in fact not possible. This is not possible. This will only be made possible if the duct is bounded. The duct, once the duct got bounded, we understood that there is an incoming wave which will get reflected because of the incident wave. It will get reflected and you will get to see a leftward or a backward travelling wave. But if the duct were to be infinite, then this B wave does not arise. That we argued pretty much the same, pretty much elaborately. Relying on that logic, the same thing happens in this spherical wave propagation problem also. Mathematically, we have understood that there are two solutions as was derived. There is an outgoing wave solution, there is an incoming wave solution. But then in this case, just like you do not have reflection in an infinite duct and thus the incoming solution does not arise. Similarly, the incoming wave solution does not arise, incoming wave solution does not arise in case of an unbounded domain. Unbounded domain, that is a domain wherein there is no boundary. However, if you can contemplate a slight complication of the same problem, that is you have a pulsating sphere, but this time this pulsating sphere is residing in a spherical cavity. You have a spherical room in which you are doing this experiment of having a pulsating sphere. So, the sphere is pulsating as before, right, it is pulsating as before, and that leads to spherical wave propagation as we understood. So, initially there will be only outgoing waves, right. So, these blue waves will travel radially outwards, and at certain instant of time it will meet the boundary which is denoted by this green line, and once it hits the boundary the incoming waves will start, right. So, the incoming waves can start only because of the boundary effect, it cannot start by itself, right, just like we had it in the case of planar wave propagation in an acoustic duct. The B wave is possible only if this duct ends in certain termination, whether it is a rigid termination or whether it is a open termination or whether it is an impedance termination. Any of these situations will lead to a incoming wave, which is basically the reflected wave which has been created after the incident wave has fallen onto this obstacle. But if there is no obstacle, then there is no chance of that incoming wave to come. So, similarly, I wish to make this remark that the incoming wave solution is triggered only due to reflections from the boundary. Okay. That is the crucial aspect, and once the reflections from the boundaries are set in, then you are going to get an incoming wave. A strange it may appear strange that once you have this incoming wave, as the wave will propagate, it will have the radial distance will go smaller and smaller, the R variable associated will go smaller. For the outgoing wave, the R variable is going larger, as a result it is going to attenuate, whereas for the incoming wave, as the wave is travelling, the R variable is going to get smaller, and actually as the wave is travelling, it will increase its amplitude in the direction of its propagation, because remember the direction of propagation of the wave, the incoming wave is inwards. So, along the direction of propagation, the wave will actually increase its amplitude. So, that is a little counterintuitive, but that is the way it is, because you will understand that as the wave is increasing, it is getting focused into a more narrow region, and therefore, the amplitude had to increase. So, this type of solution is very important in acoustics, and this solution will lead us to what is called as the monopole and dipole, which is what we will do in the next part of the course. Okay, with that we end today's class. Thank you.